we're going to focus on graphs in R. We're going to look at the lattice package and specifically the effects package, but we'll do a bit of lattice just so you can see some advanced graphing. So we're going to learn some basic R. Then we're going to learn how to import, create, and how to manipulate data. Then we're going to learn to run some models, and we're going to look at 4 types of models. So linear, logistic, multinomial logistic, and ordinal logistic, which I believe are the most common types of models used in the social sciences. Then we're going to learn how to present results and graphs using a very easy to use and very effective package called the effects package. Then we're going to talk about the lattice package, which is what effects uses, but it's very flexible. You can do a lot of different things. And it's probably the most advanced, or one of the most advanced packages that you can use to make graphs using computers. So what you need, so you need to have R Studio preferably, if you have it, it's better. The R code file, which you can download on my website, the address is here. The 2 data sets, so there's one data set called qc12.dta, and the other one is prop.csv. You should have the effects package. If you don't have it yet, if you're connected to Wi-Fi, you can download it in a minute. Just I want to make sure in case you don't have Wi-Fi. And once again, links definitely are available on this page on the website. Are there any questions? No. Okay, so we're going to start with some very basic concepts of R, and I think this is going to make it very simple, because you should understand that R is all about objects. It's working with objects. So you take objects, and you do something to it, and you create other objects. So objects essentially are computer creations that store information. So it's a bit abstract, but just think that R is something as R, what it does, it creates these objects, which are things that store information. Information of many different types. They can be numbers, they can be words, they can be graphs, they can be tables, they can be all kinds of things. And then what we're doing, we run commands on those input objects, and then we assign their output using this here. This symbol means assign, and then we assign them to output objects. So basically in each R line of code we have 2 objects. It's an input object to which we perform a command, and then we assign that output using this symbol here, to an output object. It's also important to understand that those commands in R are stored in packages. So commands don't necessarily just exist out of the box. They're not. You can't always use them right away. Sometimes you have to load a package. Some packages are loaded by default. Some of them are also installed by default. Some of them, like the effects package and actually the car package, which we will also use, you have to actually download. So the commands are in those packages. Some of them are installed by default. Some of them you have to download. That is important to know. So now, this is what we do with objects. So we take an input object. So one object, something you want to do something to this object. So let's say this is a number, and you want to multiply it by 2. So let's say this is 2. For our input object, it's just a number 2. Then we apply a command to this object, this input object. So let's say we want to multiply it by 2, so the command is multiply by 2. So we multiply our input object 2 by 2, and so it makes, what's the answer to that? 4. So we apply a command function to an object. Then what we do is we assign that. So here, the output of this is 4. So this here, what it does is it assigns it. And what it assigns it to is another object, an output object. So here, we apply this command, which in our case was multiply by 2, to our input object, which is 2. It produces something, which is the output, and it's 4. And then we assign it to another object, an output object. So our output object will now have a value of 4. So that's basically what we're doing in R. We're applying commands or functions to input objects, assigning them to output objects. Is that clear? So here's an example. So basically what we're doing when we're running statistical models is our input object is a data set interpreted in a particular way. And this is the basic syntax we use. So at the end we say, this is our data set. So data equals the name of data set. So we're telling this is our data set, but interpreted in this way. Think that there's one dependent variable regressed on, that's what this means. On an independent variable and controls, you can actually add more independent variables, more controls. Well, that's just to give you an idea of the basic syntax. So this, you can think of this as being an object. So this is a regression formula, and it tells it where the data is in that data set. But this is basically an object. It's just interpreted in a particular way. Okay? So this is our input object when we're doing a regression. Now we apply a command, a function to that object, and that command here is lm for linear model. And essentially lm, what it does is it runs an ordinary OLS regression, a linear regression. So it applies that function to this input object, which is our data set interpreted in that particular way, where y is the dependent variable, x is the independent variable, and c is a control. And that produces some output, right? So when we run a linear regression, it produces output, and that output includes coefficients, or coefficient estimates, standard errors, r squared, etc. So all of that is produced by the lm command. Then we assign that output to an object which here we call model. Okay? So is that clear? So we're applying the lm command to this input object, which is our data, and we produce output, which includes coefficient estimates, standard errors, etc. And we assign that to the model object. Okay? So that's some basic R. If you understand that, you're going to understand 90% of what we're doing in R. So now let's actually go into R. So I suggested that people use RStudio. And what's really good about RStudio is that it allows you to see a number of things on the screen at the same time. For the top of the screen, you can see your code. And at the bottom of the screen, you see an R console window. So here this is where we actually run the code. And on the right side, here you don't really see it, but on your screens you should. On the lower right-hand corner, you should see, actually I can open it. You will see a window where you can see help files, you can see the packages that are open. So help. So here, this, for example, help file, you can open packages, you can see the packages that are open. You can see the plots, so the graphs you create, and you can look at files there. And at the top, you have a history of everything you've done, and you can look at your workspace. We won't be talking too much about that. So RStudio really makes it a lot easier to use R, as you see everything sort of in one window. You can also just run normal R, and you click execute. There is also a text editor, which you can use for editing your code in there as well. But we will focus on using RStudio. Does anyone have any questions about that? Everyone is capable of using RStudio, or at least R to run the code. So you should have the code open. So here's the code file. And what we're going to do is we're going to go line by line through the code, and I'll explain it. And so hopefully everyone will be okay with that. And if you have any questions, don't hesitate to ask. I'm trying to make this as simple as possible.
It's a little smoother. We don't have run and source in our whatever you call it. Upstairs.
I'm sorry?
That's the code, right?
Yeah, but we don't have run and source. And we get that. You know what I mean?
You don't have a button for that?
Yeah.
Because no, it's fine. And you can just click on command and okay.
Or maybe
it was a 6 file.
Yeah, it should be an R file.
Yeah, maybe save it as an .r file. Okay, so let's start some basic code. So I asked people to download the effect package and actually also the car package. So the effects is a graphical package which isn't installed by default. It was created by John Fox from McMaster University, he's a sociologist who made some very good R programs. And the effects allows you to make very easy and very effective graphical displays of regression output. So in case you haven't installed it, if you're connected to the network, you can just select this line of code and click Run. And now what it'll do is it'll install it. So if you've already installed it, you don't have to do it. I'm just showing you what to do. I actually already have it, so it's not really necessary. I don't recommend you do it if you already have it. You don't have to do it, but you can. And and you can do the same thing with car. So the car package is also made by John Fox, and what it does, it contains a number of very useful statistical commands, some of which we will use today. So if you haven't installed that, you can also select it and run it. Okay?
So I have a question. So if I did my comments in R, I'll see them already in RStudio. Are they synchronized or?
Well, there are actually two different sessions of R. So if you actually have R itself open at the same time, it'll run an independent session. So the two, what you do with each program won't affect what you do in the other.
So I should close one and just
You can have both open at the same time, but they will run independently of each other. So if you run something in one version of R, it won't affect the other.
Because I install packages in R and I see them in RStudio.
Oh yeah, okay, because it's the same R, but if you install packages, that's fine.
Okay.
But if you run commands and produce output, like if you run a regression, you won't see the output in the other R, because they're two independent sessions, but it's the same installation. So if we install packages, they will appear in both.
Can we ask for your help a second?
Yeah.
To make sure we can continue. Here we have text file instead of RStudio.
Well, so what you should, this should be saved as a .r file. So what you can just do is save, go save as.
And now it's an RStudio.
Very
good. We're genius. So now we have average and good ones. That's easier to work with.
Okay, any more questions?
No.
Okay, so we'll move on. So we're also going to use a few other packages, which are installed by default. So we're going to use the foreign package, which is used to open data sets that are stored in another file format. So in other statistical programs formats such as data format or SPSS. So we can open that using the foreign package. We're also going to use the Lattice package, which is a very powerful graphics package, which is also installed by default. Just one point, you'll notice that all of these lines we've seen start with this thing here, the number sign. That basically means that these are comments. So anything starting with one or more number signs is a comment. So even if you write code and you put that after, it'll run the code, but it won't run everything after the number sign. Okay? So these are all comments. Okay, so to use any package that isn't open by default, a few of them are open by default, but most of them are not, so you have to load them. So the way you load packages is by running the library command. So library command essentially loads packages that are already installed. So if you have them installed, you can load them. So we're first going to try loading the library, the foreign package using the library command. So the foreign package, that I said, opens data sets made in other programs such as Stata and SPSS. So we're going to try loading our data now. Just before you do that, you should set the working directory of RStudio, or using R, to the directory where those files are. So the easiest way to do that is if the code file is in the same directory as where the data sets are. It's very easy. All you do is you click on Session, Set Working Directory, and then to Source File Location. And what that does is it sets the working directory to the directory where the code file is. So it's the easiest way to open files in other to open data sets, just to set the working directory to the same location where the code is. If it isn't in the same directory, all you have to do is change what's in here. So here I wrote where file is. So you can just put the directory where your data sets are, and then run this line here, set working directory, set WD, and this will set the working directory to the directory where your data sets are. So now we're going to open our data sets. So we're going to use two data sets today. And that's actually one of the strengths of R, is that you, contrary to other programs, you can actually open as many data sets as you want. So we will have two data sets open throughout most of our session this morning. And so one of them is the Making Electoral Democracy Works survey for the 2012 Quebec provincial election. So it's individual level survey data from an election. So we'll load that. So the file is stored in Stata format. So for this, we need to use that foreign package, which we just loaded. And the command to open that is read.dta. So we're applying this command to the object here, which is the file, qc12.dta. And we're just adding one argument to that command, which is convert.factors. And essentially what convert.factors does is it imports the value labels that Stata uses. So we just want to make sure we maintain those. So we use this, we add this option. So we're loading this data set, so we're running this command on the file, and then we're assigning it to an object called qc12. So now our data set, the survey data, will be in the object qc12. So all the data will be in there. If our data set were in Stata format, in SPSS format, we'd run this one instead. So rather than read.dta being the command, it would be read.spss, and you just have to add these options, which do essentially the same thing as convert.factors for Stata files. We can open files in just about any format. So we're going to open another one, which is in CSV format, which is comma separated values. We're going to have seen these types of files. So the command to open that is read.csv. So we're going to do the same thing before, run a command on that file, and then assign it to prop. So the prop data set gives two measures of disproportionality of electoral systems. One is mean district magnitude, and one is Gallagher's index of disproportionality. And we're going to use that to produce a graph towards the end of today's session. So is that, yes?
Yes, I'd like to know, because yesterday I went to the American National Election Studies website
Yes.
to download some data. And the data is in SPSS, but there is a syntax file to attribute all the labels to the data. It's like
Yes.
the original data set had no labels at all. I was wondering if there was some sort of program or would foreign be able to read syntax file from SPSS, for example. Do you know about this, or if you don't?
I believe there might be a way of doing that in R directly. Look at the help file for, we'll talk about help files at the end for the foreign package, and you might be able to do that. If not, you might have to run that in SPSS.
Save it.
Although I've worked a lot with data sets made in different formats, and often what I'll do is I'll just extract the code from those files, and I'll just apply those labels in R. It's actually quite straightforward. And actually that way, sometimes there are actually errors in their syntax files, and that way you can figure those out, and you actually get a better feel of how the data is laid out. So in many cases, I find it's actually easier and safer just to look at their syntax and see how they did it, and just copy that. You can often just copy and paste and just assign those labels directly to the variables, and it's not that much more complicated. So that's often an easier way, and you don't even need SPSS. Yes.
Would you just help me to find the data, because it seems that if I go there, I cannot.
And how do you do that?
Okay. Do you have the? Because you need to have the code. Where's the code? Did you open the code? Because it looks like you didn't open the code file.
That's prop 2.
Because you have to have the code file open to do that.
Yours?
Yeah. So this file on the top here, you have to have it
I
open.
have it.
Okay. So what you should do is just save this on your computer.
Okay.
So save this in the same file where you have the data sets.
It's in television.
Can you do it?
So I need to
No. Yeah.
yes? No?
We go back to the
Also.
first thing you do is specify what's going to be the source de la directory.
Puis là, si tu dois ouvrir le fichier ici.
Là, tu go to session.
Donc, tu vas
Ici, set open directory. And you get two directory.
So do this?
No, two directory. Then,
Puis maintenant, tu peux juste suivre.
Et là, ça va ouvrir, mais.
Donc là, tu fais ça. Puis là, juste les scripts. Fais exactement ce que je fais à l'écran. OK?
Oh,
It's on your skill. You
Oops.
yeah, you work well.
Sorry.
Okay, so everyone was able to open the data sets? Okay. So now I'm going to talk about something very fundamental in R, which is the search path. So whenever we want to access objects in R, the search path is where R looks. So the search path is a set of all the objects that are open in R. So let's look at that. So the search command, so any command has a name, and then there are parentheses, and sometimes there will be an object, or there will be arguments in those parentheses. If we don't want to add any objects or arguments, we can just leave the parentheses blank. But let's run that command, the search path, and let's see what it does. So the search path tells us where R looks for objects. So we'll see basically here there's one called the global environment, the global N, which is the first one, and that is the R workspace. That's where all the objects are that you create, and also any packages, sorry, not packages, but objects that you, so objects you create or data sets you load in will be there. So anything you do will be there. The only exception are packages. So packages that either you load or that are loaded by default will end up located here. So this tells you that R is going to look for commands in these packages, and it's going to look for objects either in those packages. So sometimes there are objects like data sets that are loaded in the packages that you can also use, or if they're data sets or objects you created or loaded they will be in the global environment, which is the workspace. Okay? Now, you can also see which objects are in that global environment. So you can use the ls command to tell you what's in there. So we've just loaded our two data sets, prop and QC12, and now they appear there. So so the first one, so we run ls without any options, without any arguments, it'll open this one. So it'll tell you what's in the global environment, and what you'll find in the global environment are the objects we have either created or loaded ourselves. Okay, let's try creating an object. So creating an object ourselves is very easy. We just put the name of an object, and then we assign that object a value. So here, this is going to be a text string. So here it's actually text that I wrote, which I just wrote object 1. So I'm assigning the text object 1 to an object called A. Okay? So keep in mind that object symbol, the assignment symbol. So it's object 1 is assigned to A. And now we'll run ls again to see what objects are in the workspace, and now we see A is there as well. So we created an object, and now it appears in our workspace. If we want to see that object, all we have to do is type in the name of the object. So either you can type it in down here, or you can just run the code, so select it and run, and we see there's our object, object 1. Now that was a pretty trivial object, so let's just remove it. So you remove objects by typing rm, parentheses, and the name of the object, and you just run that. And now we can try ls again, and we see that our object is gone. If you want to remove all the objects, totally clear the workspace, what you do is you type rm in parentheses list equals ls, so this line here, and that removes everything. Now we can check our workspace again, and we see that it is empty. So characters is actually a vector. It's a way of storing information in R. It's a type of object, and 0 means that it's empty. Okay? Since we just removed everything, we want to reload our data sets, so let's do that. The code, the 2 lines of code to do that are there. Let's just run that quickly. Now we have our data sets back.
What happens if you name another object QC12? Would it overwrite, or if you say that it's occupied?
It'll mask it, so it'll temporarily override it. So that's something you have to be careful about.
Okay.
Yeah. So you can also see which objects are in another location in the search path. So you might not want to see, so if you put ls without any objects or anything, any arguments, it essentially just gives you the workspace, which is the global environment, but you might want to see another part of the search path. So let's try ls2. So what ls2 gives you is it gives you the second object in the search path. So remember, in the search path, there was a whole list of places where R stores objects, and the second one was package foreign. So now, if we put ls2, it gives us the second one. And now it gives you all the commands, basically all the objects that are in the foreign package. So this is all loaded now. Okay? Okay, so now in R we have 2 choices for how we want to load our data sets. So there's this whole notion of attaching or not attaching data sets. So here I say to attach or not to attach. So in R you can attach data sets and basically run R the same way you would run another statistical program, meaning just using one data set. Because if you attach data sets, essentially what it does is all the objects in the data set appear in your workspace. So that can be very, very easy. It can make things very easy. If you know for sure that you only want to use one data set, then that's good. Because then you just have to access the variables by putting the name of the variable. It's very easy. So it works the same way as any other statistical program works. But as you often will want to do, and as we're going to do today, you might want to use 2 data sets. So in that case, you don't want to attach them. Because then if you attach them, you'll get confused about the variables. You might have 2 variables with the same name, like age, gender, etc. And you don't want to get confused. And you don't want variables to mask each other. So it's better, generally, not to attach. But if you're 100% sure you want to attach your data set, attach it. If you're 100% sure you want to run one data set only, you can attach it and just use the variable names without referring to the data set. If you don't attach, all you have to do is add a bit of code. So essentially you have to type data set and then $variable. So you put the name of the data set in variable. So this is the way you would access a variable if you do not attach. If you attach, all you have to do is write the variable. But if you don't attach, every time you access a variable, you have to refer to the data set. And that, it sort of makes things a bit longer, but it also makes R much more powerful because you can load as many data sets as you want. You can load many different survey data, you can load data sets, you can load data sets with macro data, with all kinds of different stuff. You can put it all together. And this provides a very flexible way of doing it because it allows you to use multiple data sets at the same time. So if you don't attach, so this is what you have to do. So now we want to access the MDM variable in the prop data set. So we type prop $MDM. So this is the mean district magnitude from that data set giving measures of electoral disproportionality. If we wanted to attach that data set, we'd type the attach command and put the data set name in parentheses. So now it's attached. So now we don't actually have to refer to the data set, we just type in MDM directly to the name of the variable, and now we get the same thing. We can also see if we look at our search path, that the data set is actually there. So prop is now in the search path. So everything within prop will run automatically, so you don't have to refer to it anymore. You don't have to refer to the data set anymore. Just be very careful that this only really works well if you're using one data set at a time and you're sure you're using one data set. Also, make sure you detach data sets when you type. So you do that by using the detach command. Is everything okay?
You said you cannot find MDM, the object, and then
You that prop, you said this?
we're going to do this. It's not.
But did you put MDM in the document?
Did you load the data set?
Because
Prop.
Prop.
You see here, prop, read, we cannot find it.
because it's not somehow deleted. Yeah.
Yeah.
So you loaded it.
Yes, and then this, no, and then, oh, not fine.
If you want to describe it from MDM was not, so I guess it was deleted from the.
I suspect that there's something wrong with this file. Try downloading the file again. Because if you look at this data set itself. Okay, you have that. Let's try to run good directly. Let's try to
Why is it all right?
Okay, try loading it again. Can you just try going through the whole thing? I mean, just loading the data set again, and then try attaching it again? No, let me know if there's a problem. We don't have too much time today, so I'll just move on, but if it still doesn't work, let me know. Okay, so now we're going to look at how we can explore data. So there's a few different commands we can use to look at our data to get a general idea of what it looks like. So one of them is summary. So the summary command would apply to an object representing a numeric variable. What it gives us are some basic summary statistics, including minimum, maximum, mean, median, first quartile, third quartile. So that's what happens if you have a quantitative numeric variable. If you have a factor variable, which is a categorical variable, is everyone familiar with the notion of a factor variable? So factor just means categorical, so the different categories. And here what it does, rather than giving you numeric statistics, summary statistics, what it gives you is our frequency. So here this variable is a type of regime, and it gives you the number of parliamentary and the number of semi-presidential systems. We can also try to get the class. We're not sure about the class of variable. Actually, running summary basically tells you that, but another way of checking is you can run the class command on a variable, and it'll tell you, for example, MDM is numeric. Okay? If you want to just get a general idea of what the values look like, one command you can use is head. Head gives you the first 6 values of a variable, or it can even give you the first 6 rows of a data set. So if you run it on a variable, what it does is it tells you, so here we have the first 6 values of the variable vote. So it tells you the first 6 responses to the question asking people how do they vote in 2012 in Quebec. And then after this, since it's a factor, it tells you the levels. So the levels are the different categories of a factor or categorical variable. Okay? If that were numeric, it would just give you 6 numbers, which would be the first 6 numbers. It could also be the first 6 lines in the data set. So if rather than running that in a variable, you'd run that in a full data set, it would give you all the variables in that data set in the first 6 lines. Okay? Okay. So now to create data, so we'll look at creating and managing data. So basically to create data, the most basic structure for storing data is a vector. So a vector, if you're familiar with matrix algebra, you probably know what a vector is. A vector is basically sort of a line of data. So you can think of it as being, so just a one-dimensional array of data. So you can think of it as being, here's an example. So here I create an object, and I assign to it one line of numbers going from 1 to 4. And the way we do that is we use the C command, which is short for concatenate. So concatenate, what it does is it brings together a number of objects, or a number. It could be a few numbers, it could be a few words, it could also be actual vectors that you bring together. So you want to bring together a few different objects and create a vector. Okay. So here what we do is we bring together a few different numbers. We join some numbers using the C command, and then we assign them to an object called object. So we just created a vector. Okay. So it's as simple as that. So rather than 1, 2, 3, 4, we can put a lot of different things. We could put words. Although even monitor words for text, you have to use quotes. Okay? So those would be strings. And if you want to see what your vector looks like, you just type in your vector, and you get you can see the values of the different elements of the vector, and so it goes from 1 to 4. When we're doing statistical analyses, is everyone okay?
Not yet.
Okay, when we're doing statistical analyses, we generally work with data sets. Okay, right? So we load our data sets, and the way R stores data sets is in the form of a data frame. So a data frame is just basically, it represents the data set. So it's similar to a matrix, but it's a set of rows and columns. So rows represent units, and then columns represent variables. Okay, so that's what a data frame is. If you want to see what a data set, what a data frame looks like, you can just use the view command. And watch out, the view command does start with a capital V, it's not a lowercase v. And that will show you in a separate tab the whole data set. So it'll give you all the rows and the columns. You can see all that. This is not for editing. This is just for visualizing. But if you just want to get a general idea of what your data set looks like, you can use that.
If we just use R, will we see that in the same way, or will it be completely different?
I believe it does run this in R as well, without R Studio.
Yeah.
Try it out, but I'm pretty sure it will do the same thing.
Okay. It's much more user-friendly R Studio, right?
Well, it helps you a lot, especially if you're going to be using code at the same time you have a code file, rather than just typing commands individually. R Studio makes it a lot easier. You can do that in basic R, but R Studio is much more developed for that. Any other questions?
Thank you.
So another way you can look at your data set, as I said before, is using the head command. So if you just want to see the first 6 rows, you type head, run that on the data set, and there we have our first 6 rows. We see the values of all the variables in those first 6 rows. Okay? So there are many different types of variables we could use, but the 2 major ones are numeric variables, and I'll just show you what a summary, actually we saw what a summary looks like, we'll just give you an idea of a numeric variable. So a numeric variable can take on basically any variable and represents numbers. A factor is essentially a categorical variable, so here we have different categories, and we have the frequencies of that. Okay, so now often people wonder in R, how do you create these types of variables? And how do you manipulate data? So often people say, well, R is difficult to do this. It's better to use another program and import your data if you want to make graphs. If you're used to making, if you're used to recoding and all that stuff in another program, go ahead and do that. But it's actually not that difficult to do in R. And it's actually quite intuitive. So we're looking to how you can make data and how you can manage and manipulate things to get what you want. Here we're going to see how to create a factor. And we're going to look at that in a couple of different ways. So one way is you can just take a numeric variable. And here the numeric variable we're going to take is age. And what we're going to do is we're going to recode it into a factor with 5 categories, 5 equal categories. So we're going to break that variable into 5 categories representing age. So it's going to be a factor with different ranges of age. So the way we do that is we use the cut command. Okay? So if you look up there, you can see cut. So we run that on our variable, which is QC12 age. And then breaks tells the command that we want to create 5 different categories. Okay? So equal size intervals. And then we assign that to a variable called AJAC, an object called AJAC. And now if we run a summary on that, now rather than seeing summary statistics of a numeric variable, here we see frequencies of the different categories. Okay? Any questions? So that's one way we can create a factor. Another way is to create, we can create a numeric variable. So here let's see what we do. So here we do basically what we did before, we created a basic object. So we just assign some numbers to an object. So this creates a vector with all these different variables. Sorry, all these different values. So here what we want is, we want the 1 to represent one thing, the 2 to represent another thing, and the 3 to represent another thing. So those will end up being representing the values of our variable. So we can just look at some summary statistics of that, see what it looks like. So it's a numeric variable at this point. But now we want to convert that to a factor. So we do that by using the factor command. So we run factor on the variable we created, which we call myVar, and then we want to create a variable called myFactor. Okay? So the factor command creates a factor variable. Now let's look at summary statistics, see what it looks like. So now we see, rather than seeing numeric summary, now we see frequency. So here it's very small, but you can see that it gives you the number of 1s, the number of 2s, and the number of 3s. But you might actually want to have labels there. You might not want it to be category 1, category 2, category 3. What you might want is for it to be low, mid, and high, low, medium, and high. So when we do that, to do that, what we do is we assign levels to the factor. So the levels are the different categories that the factor takes on. So the way we do that is we access the levels by using the levels command, and we apply that to the name of our variable here, which is myFactor. Then we assign to that the different labels we want to set. So we assign them in the form of a vector because there are 3 of them. So once again, we use the C command, and so our 3 labels are low, mid, and high. Okay? So we assign those values to the levels of our factor.
What matters the order of the...
Yes, because if you want low to correspond to 1, mid to correspond to 2, and 3 to correspond to high, then the order is very important.
So imagine you have for example, you have 4 categories, 1 is not represented in that set, and include it in your vector.
Yeah.
Group.
So you want to create a category that you don't have in your data set?
Right. Yeah, right. Just potentially the variable could take 4 categories, but in reality there are only 3 categories in that set. And if you insert a vector with 4 categories, there will be a problem. Okay, so there are 2 ways of doing that.
So what you could do is you could just add another category at the end,
Right.
and then it'll create a blank level. Or when you run the factor command, you could also add the argument. So if you to add an argument, you put a comma,
Right.
and then you write levels equal, and then you put the levels there, and you can just add an extra level.
You can specify that.
Yeah.
Okay.
And you
Yeah.
sorry to interrupt that. For since summary HF, and that was a bit before that.
Yeah.
That this previous function cut
Yeah.
would split the age variable in 5 categories of equal size.
Yeah. So there's the same number of people in each
And the
one.
size
for one.
is measured by, on the age and not in terms of number of.
Oh, so yeah, that's correct. It is. Sorry, it is the age. I believe there's actually another option which will do it based on the number of people. You are correct about that. Yeah.
And I just wanted to make
That is correct.
there may be another option where you could divide the variable in terms of quartiles, for example, and then you.
Yes, there is. To get those specific options, actually, I should have mentioned this at the beginning. But you can always use. There are two things you can use. You can use the help command. So you just type help in parentheses the name of the command, and that'll describe the command and tell you what to do. There's also the args command. So ARGS, and that'll give you the arguments you can use for a command. So you can just read up more about them and find out specific other options you can use to do exactly what it is you want to do. So I'm just going to display the summary for our new factor. So now if we run that, we get the 3 levels and their associated frequencies. So the same thing as before, just now with the labels we apply. Okay. Now I think often what we want to do is recode. So other programs there are commands which recode. That's also very easy to do in R as well, I believe. So let's make a copy of our variable because we don't want to lose it. We just want to copy it, and we'll recode the copy. So let's say we don't think there's a real difference between medium and high. So we want to combine them. So we just want it to be low and high. Okay? So what we're going to do here is we're going to access the levels of our factor, and then we're going to assign all the cases that have level the level high. Okay? So now so if you look here, what this does is this gives the levels of the factor. And now remember, so the levels here are going to be low, medium, and high. Low, medium, and high. So now if we put high for both of these, it'll assign level low for low, high for mid, and high also for high. So these two will be combined. Okay? So it's essentially recoding. And now let's see summary statistics. So now we just see our frequencies, and it's low and high, so you can check the math. 4 plus 3 equals 7, and it did exactly what we wanted. Any questions? Okay. You might also want to change the labels. You might want to change the names of the levels. So that's also very easy. So here let's copy our factor again, our variable, and let's assign some new labels. So here all we do is we access the labels using the levels, right? Using the levels command. And we just put some new names. So here there's 3 different names. So it once again it'll keep the same 3 categories. It'll just change the names. Okay, so now it's beginner, intermediate, and advanced rather than low, medium, and high. Okay, so often you'll want to change some things in numeric variables. That's also very easy to do, and actually R is extremely powerful for this. We're going to talk in a minute about something very powerful that R can do. Let's just look at this. Let's just look at this age variable. So this age variable in the QC12 data set. So we see that there's only one value of age that's really high, which is 112. So one person either said their age is 112, it was a mistake. Either they made a mistake or the coders made a mistake. But let's say we have a reason to believe that that's actually a mistake. That there was no one who was 112 years old, that really they were 22. So what we're going to try to do is change that age to 22 for that person. So first we're going to copy our age variable. So we're going to copy it from the data set to our workspace, so the global environment. Okay, so we do that just by assigning that variable in the data set to age, to just age. And now since age is not in a data set, if you just type age on its own, you will get our new age that we've copied. But if you type QC12 $age, you will get age as stored in that data set. So now what we're going to do is we're going to edit age, the age in our workspace. So it's our copy that we just created. Okay, so now we're going to look at a new type of notation, a new way of using R, which is extremely powerful. This is using indexing. So indexing is a way of accessing only certain parts of a vector or a data set, or actually any way of storing data in R. So here we have a variable which is represented as a vector, and we only want to access cases where age is 112, and we know that there's only one. So we do that by putting these square brackets. So we type age, and in square brackets we type the condition that we want to access. So here we tell R, give us age, but only give us the values of age, which are equal to 112. So it uses similar notation to other programs. So this says this is a logical statement. We put two equal signs. So I'm sure people have seen that in other programs. So you put age in brackets. You put age equal to 112. That tells R only give me age values that are 112. Then we assign to those. We assign to those values of age the value of 22. Okay. If we were going to do this for age as stored in our data set, what we do is we type this instead. So we have to type the whole, the data set, $, name of the variable, and we have to have both outside and inside the brackets. And we did also assign the value of 22. Are there any questions about that?
But isn't 195 the easiest way to do it?
I'm sorry?
Why wouldn't you go for the command in 195? Then you have solved the problem immediately. Otherwise,
Which command?
185.
Just because I wanted to illustrate working with variables that are in the workspace. I mean, we could do it that way. I wanted to make it clear to everyone that you can work with variables both that are in a data set and variables that are just in your workspace. And then there is that distinction. So if you modify something that's in your workspace, that's not in the data set, you can modify it there. But if you modify something that's in a data set, it does something different. So I just want the distinction between the two to be clear. Okay? I mean, both are valid. I mean, it's also because this is just one example. I'm not convinced that that's an error, so I don't actually want to change it. I just want to show you if you thought it was an error, it's more of a hypothetical thing. This is what you could do. So that's why I don't want to change it in the actual data set.
And if the variable is in your workspace, you can still use an regression model that includes variables that are in the data set. I mean, is it possible
Yes.
to move from one space to another?
Yes.
To use,
You just have to be careful that you don't have two variables with the same name in the workspace and the data set. Because when you run a regression model, remember we saw there's the data argument. If you add that, R will look both in the workspace and in that data set. So if you had two age variables, that could be problematic. So as long as you have variables with different names, it's fine.
and now we do
Well, now we do. So if you run a regression on this data set, using this data set, you will have a problem because we have two age variables.
it. Perfect.
Okay? So only if you have another variable, like if you have a macro variable that you want to include, you could, and it's not in the data set, you could do that.
What is the command for drop?
For drop, it means to delete something?
Yeah. When you do a mistake and you do something wrong, you just say drop.
Well, so here what we did, we copied them. So what you could do is you could just reassign, so you could just redo what we did. So let's say you made a mistake. We still have age in our data set, so you could just run this again. Okay? Right?
Yeah.
And then age will be what it originally was. So so any mistakes you made will be restored. That's actually the advantage of copying, is that if you make a mistake, the mistake is made on the copy, not on the original.
So you overwrite the copy to this again, right?
Yeah. Yeah.
Right.
And if you want to delete something, remember we saw you can either type RM and then the object's name, Or what you can do is you can assign, if you assign the value of null in capital letters, and actually I think we'll see an example of that, that'll also delete something, delete an object in R. So if you assign null in all capitals, and I'm pretty sure we'll see that, that will also delete an object. Okay, you can also index using actual numbers, so the index numbers. So you can also tell R, I want the first to the 10th line, and the first to the 5th. And I also have to mention that indexes have to be in the right dimensions. So if you're indexing a variable, there's one dimension, right? The variable is represented by a vector. So you only have to say, I want the 10th value of that variable, for example. If you have a data set, you have to give 2 dimensions for your indices, actually. You should say, you have to say, I want indices, in this example here, 1 to 10. So the colon here means 2. So I want rows 1 to 10. So the first dimension is the row. And I want columns 1 to 5. Okay? So this is another type of index. So this is actually giving the number of the rows and the columns. And you have to make sure you respect the right dimensionality. So let's see what that does. So we're telling R, give me the first to the 10th row of QC12 and the first to the 5th columns. And now we see that. The first to the 10th rows and the first to the 5th columns. So it gives you some of the rows and some of the variables. So that's indexing using the numbers of the rows and the columns. Another way, which actually we just saw using the age example, is a logical index. So that can be done, so in this example here, so it can be equals, it can be greater than, lesser than, greater than, equal, whatever. So here's one example you see in the comments. So data set variable, $sign variable, and then in parentheses you put the condition. So in our case, we want to find vote choice only for women. So the variable here is sex equals female. That's our logical condition, and then it'll give you the values of that variable, of the vote variable only for women. Now we have that. Okay? You'll notice here these NAs, and I'll just make a note about that. R stores missing data as NA. NA means not available. Okay? So that's the way R does it. So if you see NA, it means that it's missing data. So if we want to assign values to be missing data, that's what we'll do. So let's make another copy of our age variable. Okay? So we'll just do the same thing we did before. We'll override our original age copy, and then we'll make another one. Now let's suppose that rather than being sure that this was an error and that it should be 22, we're just not sure. We don't know what happened. We think maybe it was an error, but we don't know. We have no reason to think it was 22. So we just might want to make it missing data. Okay? So what we do then is we tell R, well, take age when it's 112, and assign age when it's 112 the value of NA. Make it missing. And now if we look at the summary of age, which once again, remember is a numeric variable, we'll see that there's one NA. So the NA's, the missing data will be apart, will be on the side. Okay? Let's just set it back because we're not sure about that. I'm just going to show you how to set it back. So now, if you want to tell R set any values of missing data to something, what you use is the is.na command. So that tells R for values of age that are missing, assign them the value of 112. Okay? And now we get some summaries, some summary statistics, and we see that the NA is gone. Okay? So one other thing you might want to do is you might want to change variable names. So to do that, let's create a copy of our data set. And to do that, all you have to do to change the names of variables is just you assign one figure variable to another. Okay, so here we have a variable called income in our QC data set, and we just want to assign that to another variable called SES, because we want to change the name. Okay? So now there's another variable in our data set called SES, which gives income. If we want to delete the original variable, because we don't want to have duplicates, all we have to do is we assign, this is what I was mentioning before, we assign the value of null to income, and now income is gone. So there's now no income variable in that data set. Okay? You can also change all the variable names at the same time. So let's create a copy of our other data set, our prop data set. Okay, so to do that, what we do is use the call names command. So that accesses the names of the columns, which is the names of variables of that data set. Okay? So now we have to assign a vector with all the column names in the data set that we want to create, the new column names, for the data set. So there has to be the same number of variables, the same number of values here, same number of labels of columns as there are variables in this data set. Okay? Because the column names represent the names of the variables. Now let's run that. And if we want to look, so if we just type call names, the name of our data set, we'll see the names, call names, from 2. We'll see the new names of variables in our data set. So it's ID, disrupt, mdistrict, system. Okay? So that's if you want to change all of the names of columns. You don't have to change all of them. You can just keep the original names for some of them, but you have to put a vector that has all of them because each one corresponds to a name in the original data set. Okay? Okay. We've seen how to import our data and how to create and manage it. Now let's just remove everything we've created because some of it we don't really need. So we type rm and we apply that command to list equals ls. That'll delete everything from our workspace. So everything's gone. Both what we created and also the data sets we imported. So let's just import them again by running these commands. Okay, our next thing is going to be some models, but before that we're going to take a very short break. No, 5 minutes. So let's take a 5-minute break. So at 11:44 we're going to start again. Okay? If you have any questions, don't hesitate to ask.
Okay, you're on television.
Okay, so now it's time to look at our models. So we have our data sets loaded, and we'll look at a few different types of models. We'll make some graphs first using effects, and then we're going to look at some basic lattice graphs. Okay, so first, we're going to try running different kinds of models. So first, we're going to try running models of the continuous dependent variable. So generally, the continuous dependent variable, we'd use an OLS regression. So that's what we'll do. So remember we saw before that the command to do that is lm. Okay, so we apply the lm command to this object, which is our data set interpreted this way. So with ideology dependent variable, and these are independent and control variables. Okay, and we assign that to an object called mod1. So we run that model, and we can get a summary statistics of the model itself. Okay. So you can see some basic summary statistics, pretty like regression output. That's pretty standard. The only thing is that since education here is a factor variable, this here isn't necessarily that informative, especially for testing for statistical significance. Generally, the appropriate test is the t-test. These are t-tests here. The appropriate test would be an f-test. So to do that, rather than running summary after all the models, we're just going to use another command, which is in the car package. So if you haven't loaded already, load that. And that's the ANOVA command, ANOVA with a capital A. And that will always run the appropriate statistical test for your model. So for a linear model, it'll run the f-test. For general linear models, generalized linear models like loaded, etc., it'll run a likelihood ratio test. So it'll always be the appropriate test. An f-test is actually the same thing as a t-test for a non-factor variable. So it'll always be the appropriate test. So to test for statistical significance, we can do that here, and we see that. Okay, so I didn't explain what the variables were, but here, so this is our data set for the Quebec 2012 election. Our dependent variables ideology. We have a number of social background characteristics as independent variables, and here we see that the log of income and education both have statistically significant effects. So we'll want to look at those. We'll want to graph those effects. And the way we do that is using this effects package. So we load that package. And you'll see how easy it is to make effects plots it's as easy as this, just one line of code. So we're basically running two commands here. So we have our regression output in the object mod1, and then this is the variable we're interested in. So we apply the command effect to that output. So we're telling it, take this variable from this model and create and calculate the effects. So the effects are the predicted values of the dependent variable for various values of the independent variable. And we want the variables of the independent variable of interest are log income. And then we run another command on that output, on those calculated effects, and that and the command we run is plot. And so plot, what it does, it creates a graph. So there's one short line. It's hard to see here. I'll bring this over. So we created a graph. If you're in RStudio and you want to see it in a different format, if someone wants to see it bigger, you just click on zoom, and it will make a bit bigger version of it. You'll notice here that by default, effects creates these things here called a rug plot. A rug plot just sort of gives you the distribution on that variable. In this case, it's not particularly informative, so we're going to take that off. And the way we do that is just including the option rug equals false in plots. Okay, so just run this. And now if you look at your plot, there's no more rug plot. Okay? Any questions about that?
Yeah, what was the information that the rug? I'm not sure if I said it.
It gives you the distribution on the x variable, on the independent variable. So it tells you the frequencies.
But why wasn't it like distributed?
Okay, the reason why, just the way the variable is created, because this actually it's not a real continuous variable. It was actually created from a categorical variable. I sort of cheated creating this variable. That's why it's not particularly informative. You might want to use it for other cases, but you should determine based on particular variables whether it tells you anything interesting. By default, the effects package holds other variables constant and interesting values. But we might actually want to specify what those are. So if we want to, we might want to set age of particular variable and sex, etc. So here what we're going to do, we'll tell this particular package, the effects package, calculate the effects, but keeping age at the mean, sex at female, French at true, so only we want French speakers, and education at bachelor's degree. So that'll calculate the effect for people with those characteristics. Now we run it again, and we have a plot specifically for people with those characteristics. Okay? We can also do that if our explanatory variable of interest were a dummy variable. So let's say we want to look at the effect of university education. So I created a dummy variable coded true if people have at least some university education. So let's run our new model with university instead of education. And let's run it over to do some tests. And we see that university has a significant effect at the 0.001 level. Now let's make the same plot using the same command, just university as the independent variable of interest. And we see here it creates a slightly different type of plot, but basically it gives you the same information, so you see confidence bounds for both values. You can rescale this. If you zoom in, you can play with it, make it the size you want. I know on the screen here it made it look sort of weird, but you can make that look however you want. You can make it really small, and then it'll tell you, basically whether there's a significant difference between the two values of that independent variable. Okay, so the effects package is also really good at showing interactions, which are often very difficult to illustrate in a clear way. So here we're going to interact French with log income. It's going to tell you the interaction between income and French as the first language. On ideology, so let's look at this statistical test using ANOVA. And here we see, so the interaction is here. So this is the interaction term. So so the first variable colon the second variable gives you the interaction term, and we see that it is significant at the 0.05 level. So let's make a plot. So here we basically do the same thing, but we put the interaction term in as the independent variable of interest. And now what it does is it creates a two-panel plot. So each of these is a panel, and it shows you the effect of income on ideology for French speakers and for non-French speakers. Okay? So we see that income has a stronger effect on non-French speakers than on French speakers in explaining ideology. Okay? Any questions?
Can you ever go with the browser there a little bit language to say French and change colors? Then you cannot just go in there in the kind of editor. You need to write everything down, right?
To change details?
Yeah.
To do that, you have to look at the help files. So look at the help files for effective for plot. Everything can be changed. And actually, these are basically lattice graphs. So you'd have to send arguments to lattice, but you can do that through the effect and the plots. And just look at the help files. We can discuss that if you like later. Okay. You might want to look at the other side of interaction. So the interaction goes both ways. So French. So having French as your first language conditions the effect of income, but income can also condition the effect of the French language. It might not be clear when you would use this for this particular case, but it can be done. So what we want to do here is proceed in two steps, because now we want to tell the plot function, don't show me income conditioned by language, show me language conditioned by income. But now we have to do it in two steps. So remember that we applied two functions. So first, we use effect and then plot. Now we're going to do it in two steps. So we're going to run effect, so the same as before. So on mod 3 on this variable, on this interaction actually, and we're going to assign that to this object. Okay? So it's the same thing as before, just in two steps. Rather than one line, two steps. So run that. Now we're going to plot that. But now to plot it, we have to tell plot that we want our x variable to be French. The variable we're interested in is French, not income. We have to explicitly tell it that because it will, by default, use the continuous variable. Now we run that line, and what it does is create this plot here, taking regular values of income. It breaks up. You can actually, if you specify the arguments, you can change the number of variables. Let's say, sorry, the number of values of income it takes, but it takes different values of income, and it shows you the effect of French on ideology at those different values. Okay? Now, another very common type of model we want to run is with a binary dependent variable. So, logit progress. Here we're going to run a logit. So here the dependent variable of interest is support for Quebec sovereignty. So we're going to run a model where we rest that on income, French, and yeah, and that's it. It's the same data set. Now we'll do some hypothesis tests. And so here we see this is a likelihood ratio test. So ANOVA always gives you the appropriate hypothesis test. And here we see that both income and French have a significant effect. So let's look at the effect of income on support for sovereignty. So we run the same, the same type of commands.
Yeah. Question. Here you need to for command 290. Then after you have told them about the data you will use, then you have to tell it also it's another. It is not enough to have GLM command.
Oh no, so I didn't mention this, but yes. So to run a logit, you have to use, so rather than the LM command, which runs a linear model, you'd run GLM, which is generalized linear model. And there are many different types of generalized linear models. So here we have to tell GLM that our data is of this family binomial. That's the general family of data that we're going to be using. By default, the method used here is logit, so we don't have to specify, but if you want to use a probit, you have to tell it that you want to use a probit. But here, so by default, we put family. common model code. So command multi-num applied to the data set using that formula as an interpretation of the data to use. And we assign the output to mod 6. Now let's use our hypothesis tests. So we see that both sex and French have significant effects. Now let's make a plot of the effect of French of the French language, so having French as the first language. And now we see panels for each party. So we see that support for the CAC goes up. For francophones, higher for francophones than for non-francophones. Support for the PQ also goes up, and support for the levels goes down. Is lower for francophones than for non-francophones. I'm sorry, yeah.
Usually, in multinomial regression, there is a reference theory.
Yes.
So I wonder, when you plot, what happens? What is the rationale for finding the rationale, the reference theory?
Well, I can't explain the exact mechanic, but basically this finds the probability of supporting each one of the parties.
Mm-hmm.
We can discuss the actual mechanics later.
Okay.
It's a bit more complex, but essentially it calculates the probabilities of supporting each one of the parties. Okay, so often we'll have an independent variable that is actually continuous. So here we have ideology. So we regress vote choice on ideology and a couple controls. Our hypothesis tests show that that ideology has a significant effect. Let's plot it. So now we see the effect of ideology. So voting for the CAC is more likely for people who are more on the right. Voting for the PQ is less likely. Voting for the liberals is also more likely for people who vote on the right. Okay, so now we're going to look at an interaction between university and ideology. So we want to see whether there's a conditioning effect between university education and ideology. So here our model is the same thing as we have an interaction. Let's do our hypothesis test. So here we see that the interaction between university education and ideology has a significant effect. And now let's plot that. So now we see there are 6 panels. So on one side we have cases of people who have a university education, on the other we have cases of people who don't. So it's quite similar. So in all cases, the same the relationship between ideology and vote choice is the same. One sort of interesting difference is that for the CAC, it's more of a linear relationship between ideology and vote choice for people who are who've gone to university, whereas for non-university educated people, there isn't as strong of a relationship, and at one point it sort of levels out and it doesn't really go up anymore. Potentially something that's interesting. But this time we have a graph, but it's really interesting because you can see that kind of interaction effect. Okay, now the fourth type of model we're going to look at is models with an ordinal independent variable. So a variable which is still qualitative, but with an order to the category. So it's similar to like vote choice. Similar to nominal variables, but it's actually an order. So here the variable we're going to use is satisfaction with democracy in the same data set. The command to run an ordinal logistic regression, which is the type of model we use with every variable, is pol-r, and that's in the mass package. So we have to run the mass package, load it, sorry. And now we run our model. So we run the model using the pol-r command, and we assign the output to mod 9. Again, we use ANOVA to do our hypothesis tests, and we see that income has a significant effect on satisfaction with democracy. Now let's make a plot. So plot the effect of income on satisfaction with democracy. And now we have 3 different panels, one for each category of the dependent variable. So the dependent variable had 3 categories: high satisfaction with democracy, moderate, and low. So we see that high satisfaction with democracy becomes more likely as income increases. Moderate is not really affected, whereas low satisfaction becomes less likely as income increases. Any questions about that? there's actually another way of displaying the results of an ordinal logistical regression, and that is using a stacked graph. So here you would add the arguments style equals stacked. And now what it does is it produces just a different type of graph, which looks like this. So all three categories are in the same plot. So rather than creating separate panels, it just puts them all together with different colors, and you can change those colors. The only disadvantage to this, well, some people find this really intuitive, other people don't. The clear disadvantage is that you don't have confidence bounds. But it's just another way of displaying the effects from an ordinal logistic regression. Okay, so we could also create a plot of, with the relationship between a dichotomous variable and our ordinal dependent variable. So here our dichotomous variable we're going to use is income in two categories. So let's run model 10. We run our hypothesis test using ANOVA again. And we see that income in two categories has a statistically significant effect on satisfaction with democracy. Now let's plot the effect using this. And so here it produces a similar graph, just the type of graph it creates for dichotomous independent variables. Here you probably want to make it smaller. So here you can see, so here it gives you results with confidence limits. Any questions? Okay, so we've seen the effects package. It makes it really easy to make these simple, effective graphs for showing your regression output. This package, what it uses is this very powerful package called Lattice. So Effects just creates the code to make Lattice and does it all for you. But Lattice is actually much more complex. You can do a lot of things with Lattice. It's extremely flexible. So now we're going to see, well, what happens if you want to make a more complex graph? What if you want to customize things and really get something that shows exactly what it is that you want to do? So I'm going to show you how to do a bit of Lattice. So I'm going to introduce you to some basic Lattice and show you how to make a graph in Lattice. So the Lattice package is installed by default in R. You don't have to download it, but it isn't loaded by default. So let's load it. Let's load the Lattice package. Okay? So you just run that line, library Lattice. So when you use Lattice, the most common command is XY plot, which is basically used to create a scatter plot. And you can add all kinds of things to that, such as a regression line, a Loess line. You can add labels, as we'll see in a minute. You can do it, it's very flexible. It's important to understand that Lattice works in two steps. So I'll open an example here, so you can see. So Lattice, so there's the main command, which here, for example, is XY plot. Then there's the panel function. So the panel function so the main command sets up the basic plot. So it creates, a square, let's say, and sets up the main elements, the axes and everything. And then the panel function actually does the specific things you want. So the panel function will, for example, put the points. So it basically creates a scatter plot, and you can also add a linear regression line. So I'll introduce the example. So here we're going to use our data from the prop data set. So this is, remember, different measures of electoral disproportionality. So one is Gallagher's index of disproportionality, and the other one is mean district magnitude. You should understand that Gallagher's measure is an outcome measure, so it measures disproportionality in terms of the difference between the percentage of seats and the percentage of votes parties get, whereas mean district magnitude is purely institutional. So they're not exactly the same thing, so it's sort of interesting substantively to look at the relationship between the outcome in terms of proportionality and the institutions that lead to that. Actually, it's not the only institution, there's also thresholds if you're familiar with electoral institutions. But I'll just leave it at that, just to understand what it is that we're looking at. So here's the basic syntax for XY plot. So remember, that's to create a scatter plot, is you put the command, then in parentheses, the same general syntax, which is formula, where it's the dependent variable on the independent variable, then comma, data equals plot, the name of the data set, so there's nothing really new there, comma, and what's new is you have to create a panel function. Actually, you don't have to, if you really don't want to customize anything, it'll actually create a panel function automatically, so you can actually stop here, just put a parenthesis, and then you command there, and it'll create sort of a default scatter plot. But here we want to do is we want to change the color of the points. So we're going to create a customized scatter plot, and we also want to add a linear regression line. So to do that, we actually need to create a function. So this is how you create a function in R. So this is basically an argument. So panel equals, so the argument is panel, and the value of that is equals function. And when you create a function, you tell R what the arguments are. So what are the objects you're inputting that function? So here we're just going to call them x, y. So since this is run within the xy plot is going to assign to x the name of the independent variable, which is log of MDM, and y is going to be log of Gallagher. Okay? So, and then after we tell within curly braces, we set to the function the exact commands we want it to execute, and we're going to do two. One is going to be panel.points, which creates points in the scatter plot, and we specify the argument call equals black, so that sets the color of black. By default, generally, Lattice tends to make blue points, but we're just going to set it to black. And then panel.ln line creates a linear regression line based on what we've those variables that we've inputted. Okay, so let's run that and see what happens. So now we've created a scatter plot, and we see a linear regression line. Okay? Any questions about that? So we see, if we're going to think about substantively what this means that there's a negative linear relationship between log of mean district magnitude and log of Gallagher's index, which makes sense because the larger the size of the district, the less disproportionality should be, and the more proportional an electrical system should be. Now, let's look at some other cool things you can do with Lattice. Continuing with the same example, just we'll see how you can create more panels. So one major thing in Lattice is these multi-panel plots. So we saw some of those using the effects package. So some people like to look at 3D plots. We actually show plots in 3 dimensions. Lattice, you can do that in Lattice. But we're not going to look at that today because Lattice is actually not based on that idea. The Lattice philosophy is showing these conditioning plots. So using multi-panel displays that will, conditioning on one variable, you show everything in a 2-dimensional representation. So here we're going to add a third variable, which is regime. So it's whether a system is semi-presidential or parliamentary. So this is a factor here. And what we want to do is have a separate panel for each type of regime. So the way we do that is we add this line here, and we just type regime. And everything else is the same. The only thing is that here I've changed the color of the linear regression line. So I just added the argument call equals blue. So now our points will be black, and our regression line is going to be blue. And we should have 2 panels, so one for each category of regime. So we run that, and we see that we now have 2 panels. So we see that there's a much larger slope for parliamentary regimes than semi-presidential, although this is likely explained by the fact that there isn't much variation in the mean district magnitude in semi-presidential systems. But there we have a 2-panel display. And this is what Lattice is all about. Rather than creating a 3rd dimension and creating a 3D graph, which is often very difficult to visualize, Lattice is about creating multi-panel displays where you can see the effects of different variables conditioning on another. Are there any questions about that? Okay. You might also want to add labels. There are actually a few different ways of doing this. There's another command you might want to look into. We're not going to talk about today, but identify, which actually allows you to point on points and get R to identify them. But we're not going to look at that today. What we're going to do is we're going to actually add labels to our plot. So this is going to show you what these points actually are. So each of these points represent country years. These are elections. So one will be Canada in 1997. There's Spain in 2000. We want to know what these represent. So we're going to create labels for all of these. At the same time, I want to introduce you to something else. So if you want to export your graph, because you don't just want to make it in R, you want to actually export it so you can use it in LaTeX or Word or whatever program you use. So to do that, what we have to do is we have to open a PDF device. So we're going to create PDFs, which will give you very high quality image files. So we have to open a PDF device. So we do that using the PDF command. Okay? So the PDF command you see here, so it's PDF, and then in parentheses, you put the name of the file you want, in quotes. So what this does is everything after this, and everything graphically created after this, will be stored in this file. So this opens a connection to that file, and then it stores everything after that. So once the commands that we want to store to the file are done, we have to type dev.off, the dev.off command, and that will close that graphics device. So it'll close the file. So PDF opens it, dev.off closes it. So everything between this line and this line will be stored in this file. Okay? Just a few comments on the code. So once again, we're conditioning, and we add, rather than panel.points, so rather than points, we're going to add text. So we use the panel function panel.text. Here we're going to use the argument labels. So we tell Lattice, use these labels. And our labels are equals prop country year. So it's the country and year. And here one very important thing to add is subscripts. Some of you, if you downloaded the R code before 3:15 yesterday, there actually is an error, and this will not run correctly. The subscripts here are not used. So you have to, within the function, you have to put comma subscripts, and then subscripts in square brackets after country year. The current version of the R code on my website is correct. Just there was an error. Subscripts, what it does is it tells Lattice to use the correct country year labels. So if you don't do that, if you run the original code that was on my website, what it'll do is it'll just start from the first country year and work down as many as it needs for each panel. So to use basically the same labels for each panel. But we don't want that. We want it to use the correct labels. We want Lattice to put the labels for semi-presidential systems and semi-presidential panel, and the labels for parliamentary systems in the parliamentary panel. So we have to include subscripts both in the function definition and then when we apply our labels. So let's run all of this, starting at PDF all the way down to dev off. So we run that. You'll notice that no new graph appears. That's because we opened a graphics device to save a PDF. So what you should do is open your working directory. And now, so we assigned our graph output to a file called mygraph.pdf. Now we open that and we see that there. So we see our graph is here. It's a bit crowded. There's a lot of stuff. But what we see here, rather than points, we have the names, the countries, and the years. This is mostly to get an idea of which countries are driving this relationship. So if you want to make it nicer so you can publish, you can play around with it. But now we have the same thing just to give us an idea of which countries are driving these relationships. Are there any questions? One thing I did not mention in this last command is actually I changed one option, which is CEX, and I assigned a value of 0.5. And what that does is it reduces the size of the text. CEX can actually be used for anything. It can be used for points as well. But if you want to change the size of something, you use CEX, and you just adjust that with a number. And the reason for that is when you actually create a PDF file, generally everything looks bigger than when you view it in R because it has to reduce the resolution. So often when you output to PDF, you'll want to reduce the size of it. So the argument CEX will allow you to do that. Yes?
And just so that everyone is on the same page, when you put CEX 0.5, you reduce the size of the text by an half, right?
Yes.
Yeah. So if you would have put it CX1, would not have changed it.
I believe that's correct. Yes. Is that okay? Okay. So I mentioned before, if you ever need help, it's important. You can always have help files available. In R, I have to say they're not necessarily always the most informative. Some programs do have better help files than R does, but generally, at least the command will be described and it'll give you the necessary arguments. So you can just so if you want to get access to help files, all you have to do is type help, and then in parentheses you type the name of the command. So if we want to get help on the effects package, actually, sorry, the effect command, which is in the effects package. We just type help and in parentheses effect, and that shows up here in the lower right-hand corner of our studio, and here it gives you a description, and it shows you how to use it, and it gives you the arguments. And then even at the bottom, it even tells you, it even gives you some references, and it tells you who made it, and that's John Fox and Sanford Weisberg, and it gives you their email address, so you can actually email the people who made it and tell them that you like their package or you don't like their package, or you can ask them questions, whatever you feel like. Okay, so basically that's all I want to show you for today. So let's just review. So let's just clear our data set. We don't have our workspace. We don't really have to do that, but just to review, you put rm list equals ls. That deletes everything. And now let's just quit R by using the Q command. Now it asks you if you want to save your workspace image. Generally, if you're familiar with statistical software, you don't have to do that because it's really important to code. So let's just do no. So we don't want to save the data, and then just closes R or our studio. If you have any questions, feel free to contact me. My email address is actually in our studio, so you can go back there and close it. If not, you can just get it from my website. Feel free to ask me any questions if you see me. I'm always happy to help. If you want to learn more about R, I'm just going to give you some ideas. There are two very good books. One is sort of basic. This is John Fox's book. I know it's sort of hard to see here because of the screen. It's called An R Companion to Quadrant Regression. This actually goes with his regression book, but you can use it on its own. It's a very good book, relatively easy to use. It actually, the effects in the car package are sort of explained very well in here, and the car package is actually the package made for this book. But it's a very good introduction to R. It's very complete. It's about 500 pages. I don't think it's too expensive. If you want to get a bit more advanced, another really good book is Modern Applied Statistics with S. And you might be wondering, by Venables and Ripley, you might be wondering, well, I want to learn R. Why am I looking at S? And actually, so you understand exactly what R is actually a statistical whole environment based on a programming language, a computer language called S. So the basic language, what we've been seeing is actually S. So all the syntax you've been learning is S. It's not actually R. R is just a statistical environment based on S. There's actually, so R is an implementation of statistics for S, using S. There's actually another one called S+, which is a commercial version, but it sort of isn't really used too much anymore because R is open source, it's free, and it's become very widely used. So you might want to know that S is the basic language behind this. And so if you want to learn more advanced stuff about the language, you can use this book, Modern Applied Statistics with S. You can order it on Amazon, or they have it at the library here, although I currently have I believe the only copy of it. But if you want to look at it, ask, I will actually return it. So that's it. So does anyone have any questions? Are you all ready to use R? No one has any questions? No comments?
You know I have questions in the future, right?
Yes, I'm looking forward to your questions. Anyone else? Okay, so that's it.
Thank you.
Thank you.